This video is going to be about percent of change. So first of all, with percent or change, we're either increasing or decreasing, and that's easy to see. If we're increasing, we go from a smaller number to a bigger number, so 4.3 to 8.7. Decreasing would just be the opposite direction. Decreasing would be we start at a big number, 8.7, and go to a smaller number, say 4.3. So both of these, if we want to find the percent of change, then we actually use the same formula. We do the amount of change divided by the original amount. And that'll give us a decimal. To make it a percent, we just times that by 100. So our first one, if we're going to increase from 4.3 to 8.7, we want to find the amount of change. We do that by subtracting. So I would do 8.7 minus 4.3. But we're going to divide by the original. Well, we started with 4.3. That was our original amount. So we'd end up dividing by 4.3. This decreasing one, we'd still have 8.7 minus 4.3. That still gives us the amount of change, but instead of dividing by 4.3, this time we would divide by 8.7. Now when we go plug this into a calculator, we need to figure out the top part of these fractions first. We want to get that subtraction done, and then we can divide. So 8.7 minus 4.3 is 4.4. So we will do 4.4 divided by 4.3, or on the second one, 4.4 divided by 8.7. So 4.4 divided by 4.3 is 1.02 times, or 1.023. And then we have to times it by 100 to make it a percent. This would be 102.3%. So that's how much we increased by. And that makes sense because we went 4.3 to 8.7 was 4.4. That's all of 4.3 plus a little bit more. So all of 4.3 would be that 100%, plus a little bit more would be that 2.3 extra percent. So then we would do 4.4 divided by 8.7 to do the decrease, which would be 0.5057, timesing by 100 to make it a percent would be 50.57. And then usually they want you to round to the 10th place. So looking at the number next to 5, that's a 7, that means we're going to round up. So it would be 50.6% decrease. So increase over here, decrease over there. So I wanted to do them side by side so you could see that, well, the beginning part is the same, but what you divide by is different. We divided by 4.3 because that's what we started with. Over here we divided by 8.7 because that's what we started with, which makes your answers very different. So second, they talk about greatest possible error of a measurement, or percent error of a measurement. I'm going to do those side by side again. So greatest possible error and percent error of a measurement. Both of these are for a measurement. So if I had a ruler and I was measuring something with that ruler. So I'm going to draw a ruler. It's not going to be great. And I'm just going to put in the inches. It depends on what unit we are measuring to determine our greatest possible error. So I just put in inches. If I had put in the little tick marks in between and had like 2.1 inches, 2.2 inches, so on, then we'd have to do this a little bit differently, and I'll show you that as well. So if we're just measuring to the nearest inch, so let's say I'm trying to measure 2 inches. The greatest possible error is how close to 2 you can get so that when you round, it would round to 2. So if I measured, for example, and I said, oh, let's measure right here. I don't know why it keeps coming up with that extra box when I'm trying to write. 1.2. 1.2 would round down to 1. So that's not part of the greatest possible error. We want to just include the numbers. And I'm actually going to get rid of that so we just can't see it anymore. We only want to include the numbers that would round to be 2. So if I took 1.5, that and everything above it would round up to 2 inches. If I took 2.5, that and everything below it would go to 2. If I got any higher than that, then we'd start rounding to 3. So we only want to include everything above 1.5 and everything below 2.5. So the total distance of this error, if we're going from 1.5 to 2.5, that's 1 inch of error. But we only want part of that. We want just the halfway, because we could go halfway up or we could go halfway down. So the greatest possible error for just plain old inches would be 0.5 inches, because that would take us up to 2.5 by adding 0.5 here to 2, would take us down to 1.5. Same idea if we were using smaller measurements. Let's say, now I'm going to increase and say, okay, this whole thing is 1 inch. And so what if we went by tenths? So we have 1.1, it's going to be really hard to label, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7. I'm not labeling every one of them because I just can't physically write it in. 1.8, 1.9. So again, if we're measuring to a specific unit, let's say 1.7, we want everything that would round up to 1.7 or down to 1.7. So since we're being measured, our units are in the tenths. We're going point something. This time we're going to do it algebraically instead of a picture. So we're going to the tenths. Tenths are the first decimal place, so 0.1. But we only want half of that. Just like this 1 inch was the entire distance of error, we only want half of that because we just want how much would we have to go up or how much would we have to go down from 1.7. So if we divide this by 2, we get 0.05. That is my greatest possible error. Now if they ask us for percent error, that's asking us something different. So to find percent error, we're actually going to have to use the greatest possible error. Percent error is the greatest possible error divided by the measurement itself. And greatest possible error should all just be the top of that fraction. If I were to use an abbreviation, because I can't write the greatest possible error in that space, it would be like this. So percent error, let's do an example. Let's say we want to find the percent error of the measurement let's say that our measurement is 23 inches. So first we have to find the greatest possible error. Well, we just look at our units for that. Units wise, we're measuring in the ones place. So if we're measuring in the ones place, our unit is 1 inch, and we divide that by 2, we cut that in half to get 0.5 inches. That's our greatest possible error. I'm just going to keep using GPE for greatest possible error. To find the percent error, we're going to take that greatest possible error and divide by our original measurement. So we're going to take 0.5 divided by 23, which is 0.0217. We are going to multiply by 100 to again make it a percent. So timesing by 100 is 2.17. Usually they want you to round to the tenths, so 2.2%, or if they had wanted you to round to the percent, then it'd be 2%. Now if we took that same question, find percent error of the measurement, and this time instead of doing 23 we said 23.6. Now the place that we're measuring to, the units place, is tenths. So now we have 0.1. Again, we still have to divide that by 2, so 0.05, and we still divide that greatest possible error by the measurement itself, so 0.05 divided by 23.6 is 0.00211 times 100 again is 0.21%, or most likely they would just put 0.2%. So I'm going to just try one more. These ones are kind of a little bit weird. So again, we're going to find the percent error of the measurement. Let's make it something a little smaller this time. Let's say our measurement is just 0.3. So again, we have to decide what units place we've gone to. Are we in the tens, the ones, the tenths, the 100ths? Depends on where our last digit is. Well, our last digit is the 3. It's after the decimal place, so again, this is tenths. We still divide it by 2, so you're going to be using the same number a lot, which we already know is 0.05. So 0.05 divided by 0.3 is 0.16 repeating. If we multiply that by 100, we'd get 16.6 repeating, or 16.7. Or if they wanted you to round to the ones place, then we could say 17% instead. Hopefully this video is helpful. If you have any more questions, please let me know.